Hey students, it's Mr. Otto with inverse trig functions. That is our new lesson today. So here goes nothing. So a couple things to recall. Inverse functions are operations that undo the other one. So anytime like you're solving an equation, it's like 2x plus 1 equals 9. When you subtract 1 from both sides, you're doing an inverse operation. Those cancel, you get 8 equals 2x, and you divide by 2. Those are inverse operations. Cool. Uh, the function f of x equals x squared, when we restrict it to be x is greater than or equal to 0, has an inverse function that is the square root of x. And that's because, if we remember, that's the graph of x squared from 0 to infinity, and this is the graph of root x. Similarly, cubic functions and cube root functions. The nice thing about cubic functions and cube root functions is they are both one-to-one. If I had graphed the other side of this part, you would notice that, of the parabola there, you would notice that, oh, those are not one-to-one. And the reason that is important is because a function that is not one-to-one does not have an inverse that is a function. So I'll say that a different way. If a function is one-to-one, we know that its inverse will also be a function. However, when I do the whole square root, that's not a square root, that's a parabola. When I do the whole y equals x squared, notice that its inverse would end up looking like this. And that, so you get, y equals x squared, and here you would get x equals y squared. That is obviously not a function. So what we have to do at times is we have to restrict the domain. I guess I'll just leave that stuff up there. See, yay, cool. Um, so that's kind of what this part's talking about. If a given function asks to find the inverse, well, yes, we already know how to do this part. And remember, the domain of f is the range of f inverse, and the range of f is the domain of f inverse. And as always, if you do the composite function where you plug f inverse into f or f into f inverse, you should always get out x, which is the line of symmetry that they are flipped over. So let's talk about sine of x. Obviously, no, the sine of x is not one-to-one because notice if I do the horizontal line test, oh, that's that. Also, if I went to say, let's go to Desmos. Where's Desmos? Desmosidator. There's Desmos. So if I did here the sine of x, we got that. And so let's do, so now what happens when I do that exact same function, but I do the inverse and I do the sine of y? Oh, it doesn't like that, so let's do this. Do x equals the sine of y. So notice, and if I have the line y equals x, those are, you know, reflected over that. Now, if I look, the sine of y is not a function. Um, so, that's the blue line right here. We notice that is not a function because it does not pass the vertical line test. And we know that sine is not one-to-one because it doesn't pass the horizontal line test. So what we're going to have to do is we're going to have to restrict the domain of the sine function to figure out what its inverse would look like. So let's go do that real quick, and I'll go back to here. So if I look, okay, well, there we go. If I look, um, essentially what I want is to restrict my function so that only part of it, the only, like we get a one-to-one part, and I want as much of it to be one-to-one as possible. And so here, let's make that big up. And so if I look, I'm kind of highlighting where we could end up going. So there's all these extra parts right here. Notice, um, and so, ooh, let's do hot pink. I like hot pink. Okay, so you see these different colors. You see the pink, the red, uh, the green, the purple, the green, the purple, and the like salmon color. What we will typically do is we pick one of those. And um, being that we like things centered around the origin, uh, we're going to look at essentially this area in here. Okay, so this is where we're going to restrict the domain of sine. Okay, so when we restrict the domain of sine, we're only looking in between negative pi over 2 to pi over 2. So typically, right, our domain for sine is all real numbers, and our range is -1 to 1. Well, what we're going to do is let's look at the restricted. The restricted version would be negative pi over 2 to pi over 2 and -1 to 1. Now, the reason we look at just this part, like I was saying, is it's centered about the origin. Um, it it's that's where we're gonna look. I mean, we could have picked any of the other parts, um, but that's the one that generally we use because when you that's what your calculator ends up giving you is some value between these two when you use the inverse of sine. So if we said, hey, let's flip this over the line, y equals x, and I don't really like how that worked out, so let's do this. That is probably fine. Maybe actually, I don't even know. With that line would its the axes are different. -1 would be here, it's -pi over 2, so probably more like doesn't matter. So what we would do is we would flip that over the line y equals x. So here we're going to look closer at um, that restricted domain. And what I'm going to do is I am going to reflect this over the line y equals x. Um, which is here. I need to draw a line kind of like that. Um, Okay, so we're going to reflect over that line, and what we'll see is we get some other function, junction, and it goes like this. No, that was not supposed to go straight like that. And we get this, and kind of follows that, and it goes up. So that's our inverse sine. So it looks like that. The other thing you might see, y equals sine inverse of x. It is also called arc. That's arc sine of x. Now, one thing to note is if I'm right here, that -1 does not mean sine to the -1 power. It means the inverse of sine. So I know we write like sine squared x or cosine to the fourth x, but whenever you see this, it is not 1 over sine x. That is not true. So same thing with any of the other um, inverse trig functions. So if we look right here, right, I notice we had the domain of sine was from negative pi over 2 to pi over 2, and the range was negative 1 to 1. Well, notice the range, so like the domain of y equals sine inverse of x is going to be negative 1 to 1, and the range is negative pi over 2 to pi over 2, which should make sense because all we're doing is just Zipperuskiing those. And the domain of the inverse is the range of the original, and the range of the inverse is the domain of the original. I think I just said the same thing backwards. All right, so let's talk about inverse sine. The inverse of f of x can be written as sine of y, which that's this blue function right here, right? We can also come in and be like, okay, I'm gonna let y equal, and then we go to our functions and we are like, yeah, we do the inverse sine, and oh, look at that. It lies perfectly on top of that blue one. And if I take away the blue, let's just take away the red as well. Let's take away the blue. Oh, blue's off, blue's on, blue's off, blue's on, blue's off, blue's on. And notice there's your inverse sine function that just lays on top of uh, sine of y. Cool. So back to this. Um, so the inverse of sine can be written as x equals sine y, which is not, that just gives you the something that's not a function. Uh, or we can write it as, like I said, arc sine of x or inverse sine of x. And the domain of sine of x, well, we already kind of did all this, was negative, um, that we restricted it to was negative pi over 2 to pi over 2, and the range was negative 1 to 1, which then I just, do copy because, paste. Oh, so then that'd be the range there. It's just easier to write it. So notice, oh, look, there's our inverse function. Um, so we're looking at the function. Yeah, that's what it is. Um, cool. So now let's talk about, like we said here, domain of sine inverse. It's negative, no, it's negative 1 to 1. And the range is negative pi over 2 to pi over 2. So if I come back here and I want to look at, okay, where's pi over 2? Well, let's get our handy dandy whiteout out and let's do this. Okay, no longer are we pi over 2. Y'all, we're not going to use uh, degrees all that much. So, and I color in these white parts. Yeah, they're gone, gone. Cool. So, now we are going from negative pi over 2 to pi over 2. Okay, so this is now negative pi over 3, not 6. Negative pi over 4, negative pi over 6. And then, we've got 0, pi over 6, pi over 4, pi over 3. So for the function arc sine or inverse sine, we're really looking at values along here for the inputs and outputs. So like if I said arc sine of negative root 3 over 2, I would say, oh, that's negative pi over 3. And that is the only possibility if I did arc sine of negative pi over, not pi over 3, negative root 3 over 2. The only possibility is negative pi over 3 if we're talking about the function. Cool. And so those are the only values we can use. Um, great. Now, let's just do some examples. I really wish that had parentheses around it right there. Let's put some parentheses in. It should be like that. Okay, so, oh, hey, we just talked about that one. That's right here. And we know that's actually negative pi over 3. So negative pi over 3 would be our answer. Arcsine of root 2 over 2. Well, arcsine of root 2 over 2, that's going to be pi over 4. Because if you think of our triangles, right, we're really just looking at the vertical part. Okay. And then, of course, arcsine of 3. Well, let's look where 3 is. Again, like I said, we're only looking at this part right here. Arcsine of 3, well, 3 would probably be like somewhere over here, just because that's close to pi. And notice that is not in our domain. So DNE outside the domain. Cool. All right, now let's talk about cosine. We're gonna talk about cosine. That's weird. Not really. So again, like I was talking about, we can look at different parts. We can look at here to here. We can look at, oh, I meant to change the color, and you did not change the color. There we go. There to there. We could look at, that also didn't change colors. Okay, there we go. Here to here. And what we're going to end up using is the positive part. So like in here. So we're going to be looking at this part of cosine. And, okay, so I probably really want that to be yellows just to kind of go along with the color scheme that I've got going on here. You know, gotta match the color scheme, right? Okay, so we're looking in that area. And so if we notice, right, typically our domain for cosine is all real numbers and our range is -1 to 1. But if we restrict it, notice I'm restricting from 0 to pi. So my restriction for cosine is going to be 0 to pi, and it's -1 to 1. Is the function 1 to 1? No, but we already knew that because it's just a shift of sign. Um, so let's go and talk about arc cosine. Okay, well, we know the domain of cosine on this little area is 0 to pi, like so our restricted part, and our range is -1 to 1. So that means the range of arc cosine of x, which is also cosine to the -1 of x, or inverse cosine, is 0 to pi, and the domain would be -1 to 1. Okay, so like we have right here, there's that and that. Now, we are just going to be looking at 0 to pi right here. Okay. Um, okay. So we'll just be looking from 0 to pi. So we're going to be only looking in quadrants 1 and 2. So quadrants 1, quadrant 2. Cool. So let's look at some actual values. If I look at cosine inverse of -1, well, where is cosine -1? It's over here at pi. So that would equal pi. So remember, the thing when we're doing like inverse sine or arc sine, we're saying, okay, if this is the side length here, what would be that angle measure? So the way I often will think of this is, okay, cosine of x is equal to -1. So what value for x gives me -1? Or what angle measure? Well, that angle measure would have to be pi. Uh, so that's kind of the way I think of these problems. Again, here, cosine of x equals √2. Um, well, if I think about it, root two is larger than 1. Um, and cosine can never equal that. So what I would say here is dne, because it's outside domain of inverse cosine or arc cosine. And then arc cosine of 1/2. So I come here. Arc cosine is 1/2. When, we're at the shorter end of our little triangle here. So that is 1/2 here. So that's when cosine of pi over 3 I know is 1/2. So arc cosine of 1/2 should be pi over 3. Cool. All right. The last one of these we're going to look at is going to be tangent. Um, so if we look at arctangent, hey, can you kind of see where tangent has a little thing here that's, you know, it's 1-to-1, or we can like restrict it? Good, I'm glad. It's going to be just along here. And I'm going to restrict it between -pi/2 and pi/2. Yay! Cool. So we're restricting there. Um, so if I look, right, the domain of that restriction of tangent would be -pi/2 to pi/2. And I'm putting parentheses because it's not inclusive. And the range is going to be -infinity to infinity. So that means the range of tangent inverse is actually going to be -pi/2 to pi/2. And the domain is -infinity to infinity. So you can kind of see here, this part, this is your arctan graph. And notice there are two asymptotes at y equals pi/2 and y equals -pi/2. Um, and they will not cross that. And notice this is kind of similar to what we had for arc sine. And so just like with arc sine, I'm going to be looking at this part right here. And we're really going to be looking at, I'm going to call this now -pi/2, -pi/3, -pi/4, and -pi/6. I'll just call it 0. So that's kind of what we're looking at. We have the domain of arctangent is -infinity to infinity. So we can plug in any number. However, the range, we can only get out values between -pi/2 and pi/2. Cool. So here, let's look. Okay, like I said, we're only looking at these parts right here. And let's do this. So -1, tangent of -1. Um, so the thing that I have to remember, right, is tangent is the opposite over the hypotenuse. Nope, that's wrong. The opposite over the adjacent. So this is negative root 2 over 2, and this is root 2 over 2. Well, when I divide those two, I get negative 1. So that is basically, I'm asking, when does tangent x equal negative 1? Well, that's going to be here at negative pi over 4. Ah, when does arctan equal root 3? So over 2. Nope, just root 3. So again, let's do this. Okay, root 3, we want um, to be, not that one. We actually want this one right here. We want it to be longer down than it is tall, but it's not going to be that angle because that would be negative. That's nice. So we're going to look here and here. And I know, oh, that's root 3 over 2. This part's going to be 1/2. You know what? I'll erase this root 2 over 2 so it's not in our way anymore. And I can say, okay, opposite over adjacent. Well, that's root 3 over 2 over 1/2, which is just root 3. So arctangent is going to be, of root 3, is going to be pi over 3. And that's because, tangent of pi over 3 is root 3. Um, all right. Tangent of 3/2. Um, well, let's look at where would this one be. Ah, so if I look, it's not one of our values on the unit circle. So you're going to need a calculator. So let's just, let's go over to Desmos because it's going to help us out the most. So I go to functions. I do the tangent. I do 3 divided by 2. I get 0.98279. And let's just make sure we're in radians. Look, if I did degrees, it would say 56. But we're in radians. So I'm going to be 0.98 root 2. Just going to go to 3 decimal places. So 0.982. You need a calculator for that one. Okay. So what quadrants do I care about? Well, here's kind of how I think about it. Um, the way that I think about it is like this. Okay. I have cosine here and sine along there. So negative pi over 2, 0, pi over 2, and pi. So notice you got cosine and then sine. That kind of tells me what part I use. Um, for tangent, that's actually not correct. So you've got cotangent will actually be 0 to pi, and tangent will be right there. And then um, for like your arcsecant and secant, you have secant, cosecant. So what's really nice is secant and cosine, they're going to have the same range, and cosecant and secant are going to have the same like values you can get out. Uh, and so you can kind of remember like what parts of the um, unit circle you can use using that idea. Right. So what happens if we have arc secant of x? Um, well, we just flip the ratio, flip the function and ratio back into appropriate reciprocals. All right, like I was saying before, we were rudely interrupted by me pausing it, which y'all have. Y'all can't even tell probably because it doesn't even feel like it was a pause. All right, maybe I should cut this part out. Who knows? All right, back to this. So essentially with secant and cosecant, we're just going to flip uh, the argument. Remember this part here, that's the argument. I'm going to flip the argument and make secant inverse of x be equal to cosecant inverse of 1 over x, since they are reciprocals, right? So if you think of it like this, if I have cosine x is 1 over secant x, or even secant x is 1 over cosine x, if they equal, um, you know, say 2 over root 2, because, well, they say we equal 2, because remember, say I'm looking at, oh, I don't know, let's do pi over 3. Secant of pi over 3. Hey, cool. Secant of pi over 3 is going to equal 2, because cosecant, or cosine of pi over 3 is 1/2. And so if I did this, secant inverse of 2 over 1, well, that should equal cosine inverse of 1/2, which is pi over 3. So that's kind of how I'm going to handle that. So I take the original, right, and I write b over a. Um, Now, that will work for secant and cosecant x. However, with cotangent, remember the thing about cotangent is the range is 0 to pi, and our domain is negative infinity to infinity. So with cotangent, we actually just have to use it as is. So we're not going to flip the argument there. We're just going to be like, okay, if I have cotangent inverse of, not pi over 3, of root 3. Well, cotangent of x is equal to root 3. Well, that would be root 3 over 2 over 1/2. So if I remember, cotangent can also be written as cosine x over sine x, which is, because it's the reciprocal of tangent, which is sine over cosine. And cosine is equal to root 3 over 2 at right here at pi over 6. Cool. All right. And that's how that works. So let's look at some examples. Cosecant. All right. So what I'm going to do is I'm going to change this to be sine inverse of 3 over 2 root 3. So I'm going to multiply by root 3 over root 3, which, if I look, that's going to end up being 3 root 3 over 2 times 3. So it's really just sine inverse of root 3 over 2. Well, sine inverse is root 3 over 2 when vertically we're taller and horizontally we're shorter, so pi over 3. So that's when cosecant would also equal that. Arcsecant, negative root. Oh, but that's a negative value. I forgot the negative, y'all. My bads. So that'd be just negative pi over 3. So to be over here. And remember, this is really negative pi over 3. Negative pi over 2. Negative. There we go. All right. Cotangent. We'll come back to that one. Arcsecant. Well, it's the same as arc cosine if I did -1 over root 2? Well, let's multiply by root 2 over root 2, and we get, oh, what is this? My, as if it isn't the multiplication of two fractions. -root 2 over 2. Oh, well, that happens when cosine's at 3 pi over 4. Because remember, it goes cosine. So cosine is 0 to pi for our range. Now, cotangent, -root 3 over 3. Well, that would have to be when, so cotangent is -root 3 over 3. That probably means we had a 1 over root 3, which really is 1 over 2 over root 3 over 2. And if I remember, cotangent of x is equal to sine x over, nope, cosine x over sine x. Cool. So essentially looking where does cosine 1/2, and that's when we're a little bit shorter here. So it's going to be at pi over 3. All right. That's how we kind of do those. Here's some try on your own problems for you to practice. I want you to do those, and we will go over them on Thursday in class after St. Andrew's Day. Okay, so let's kind of sum it up. The domain for arcsine, right, is going to be -1 to 1, and the interval for our range that we're going to be looking at is -pi over 2 to pi over 2. So remember, these are the side lengths is the domain, and the range are the angle values. Arc cosine is -1 to 1 and 0 to pi. Arctan is the domain, it's -infinity to infinity, and the range is -pi over 2 to pi over 2, non-inclusive. Arcsecant, um, well, arcsecant is going to be -infinity to 1. That's not right. It's a -1. And then 1 to infinity. Just remember, that's the range of secant or cosecant, so that would be the domain of arc cosecant or cosecant inverse. And then your interval will be -pi over 2 to pi over 2. Arcsecant is going to have the same as arc cosecant, except we're going to be from 0 to pi. And so we're looking at quadrants 1 and 4, quadrants 1 and 2. Just remember here, though, we're looking at negative, that in the quadrant 4, we're not looking at, 5 pi over 3, we're looking at -pi over 3. Arctangent is 1 and 4. Arc cosecant is also 1 and 4. And arcsecant is 1 and 2. Arc cotangent is going to be -infinity to infinity, kind of like tangent, and then 0 to pi, but not inclusive because sine of pi is 0. And we're looking at 1 and 2. So the other way you can think of it right is cosine, cotangent, secant, cosecant. And that is your lesson.